Okay, if a relay coil containing 27 ohms of resistance draws 0.55 amps of current when energized with 24 volt 50 Hz AC supply, calculate its inductive reactance. So we're going to do this and answer it in ohms, of course, rounded to 2 decimal places. Okay, so it can be a bit difficult sometimes to know where to start when you're just presented with a big chunk of writing like this. So what I'd suggest to do is read the question as closely as you can and see if you can interpret the numbers to then draw yourself a circuit, because as soon as you do that, things become much more visual and I think easier to know where to take the next step. So let's see if we can do it. The first thing we need to look at here is the fact that we are dealing with a relay coil. And relay coils are going to, as it says in the top line here, contain some resistance, 27 ohms in this case. And they're also going to contain some inductive reactance, because the relay coil is a coil of wire. So any piece of wire firstly is going to have some resistance, but by virtue of it being coiled up, that's going to mean it's got some inductance and therefore inductive reactance. So we can interpret this as being essentially a series circuit containing resistance and inductive reactance, which from our notes and this topic we should understand is what we call a series RL circuit. So you can just start by drawing your circuit. Okay, here's our supply. I'll pop that in with a resistance in series with an inductance. So we should recognize that pretty quickly as the things we've been looking at in other questions. Okay, let's see if we can read the question now and take some numbers off it and pop it onto the circuit. So first up, we've got resistance of 27 ohms. So I'm going to write that value above our resistance. R is equal to 27 ohms. Okay, what else do we know? We've got a current of 0.55 amps. So I want to make a little list of all the values that were told in the question down the left-hand side as well. 0.55 amps. So we're energizing this with a voltage of 24 volts. So V is equal to 24 volts. Probably also a good idea to take that voltage and just chuck it underneath your supply. We've got a frequency here of 50 Hertz. So F equal to 50 Hertz. And again, you can pop that 50 Hertz value underneath your supply. We're trying to calculate the inductive reactance here. So inductive reactance always has the symbol of XL. So we'll write XL is equal to a question mark and also put our XL value up on top of our component. So question mark there. One other thing when you're looking at circuits like this that are specifically dealing with a relay coil, or it could be a contactor coil, or it could also be a motor winding, you often see them drawn with a set of like dashed lines like this around the two. And the reason for that is because we have one component that we're looking at here, but that component contains two quantities. In this case, some resistance, and it's also going to have some inductive reactance. So we draw them within these dashed lines to say that those quantities are contained within the one component itself. All right, now we've got our circuit. Let's have a look at how we might solve the thing. So we'll start just by looking at one thing you're probably likely to do is just pick up your formula sheet, see if you can find a formula here to solve inductive reactance. So if you do that, you'll see that you get to a point where you know that XL is equal to 2 times pi times the frequency times L, which is the inductance. This is actually no good to us because you'll hit a dead end. Even though we know the frequency of 50 Hertz, we don't know anything about the inductance of the component. So this is actually no good to us. You'll never get the answer going down this path. So what you've got to do is probably then see if you can find any other method of calculation or formula or whatnot that contains inductive reactance, and that's the next place we can go. So if you look through your notes, you'll see that you get to the point where you can find the impedance triangle. The impedance triangle, we've got a little phase angle in there. We tend to use this to help us to solve the impedance, which is the hypotenuse of our triangle there. We've got a resistance over here, and the inductive reactance would be on the opposite side, the vertical component. So yeah, we would usually use it to solve the impedance, but we can also use it to solve another side if we know the other two sides. So if we think about this a bit closer, we've actually got the resistance here. That's 27 ohms. Obviously, we're trying to find the inductive reactance. We don't know that. We don't yet know the impedance here, but can we firstly do a calculation to work out that impedance and therefore use that value to then use Pythagoras to solve the remaining side of our triangle? That's what we need to do. So the next thing you've got to do is pick up your formula sheet, see if you can find a formula to solve impedance Z using the values that you were given in the question. And you'll see that you actually get to the point where you can find Ohm's law to solve for impedance. So Z is going to be equal to the voltage divided by the current. As you can see, pretty straight up Ohm's law. So we've got the voltage, we've also got the current, so we're ready to go. Let's substitute our values in. We'll go Z is equal to 24. Divide that by your current of 0.55. And that's going to give us a value of impedance as 43.64 ohms. So there we go. We've just worked out the impedance, so we can put this value onto our triangle. And now it's going to be a bit easier for us to work out this side of the triangle because we've got the other two sides. So all we're going to do now is just use straight up Pythagoras to do so. So it's going to be XL will be equal to the square root of Z squared minus R squared. Remember, I'm using minus here because we're trying to find a side that is not the hypotenuse. We're looking for another side. So we can then just substitute our values in. So we've got the square root. Our impedance we've just found is 43.64 squared minus the resistance we were told in the question of 27 squared. And if you do that correctly in the calculator, you'll get an inductive reactance of 34.28 ohms. So there you go.